Well, hello, my name is Achilles Kapis. Together we will go through a brief introduction to the physics of sound. We will try to describe sound and briefly discuss why we study it, why is sound important. We will go through its basic characteristics and finally see how it behaves. So let's get started. What is sound? Although this is not an exact definition, we can say that sound is oscillations of some quantity, such as pressure or particle displacement, propagating in a medium with internal forces. Sound manifests as waves and is distinguished from optics in that sound is a mechanical wave motion. In fluids, sound is mainly a longitudinal wave, like this one shown in the animation, where medium particles oscillate in such a way that create compressions or rarefactions, propagating along the same direction with the oscillations. This is an example of a propagating pressure wave in gas, like air. In solids, it is possible to encounter more complex types, such as transverse waves shown in the second animation. Here the particles move perpendicular to the direction of the wave propagation. This could very well represent the displacement of the particles of a vibrating string. At this point, it's important to mention that acoustics, which is the field that deals with the study of sound, is concerned with the macroscopic behavior of the structural motion of a bulk of medium particles. Although the first animation here shows distinct particles, they should in no way be considered as such. The motion of individual particles is chaotic in nature, while their collective motion exhibits structure with clear, distinctive characteristics. The applications of sounds are numerous and range from engineering, dealing with noise mitigation, arts and entertainment, where electroacoustics, for example, deal with the design and implementation of transducers such as microphones and loudspeakers, room and architectural acoustics, medical applications with an example being the ultrasonic monitoring, such as the image we see from the baby down there. Bioacoustics that deals with the hearing mechanism, as well as the emerging field of acoustic ecology. The list is almost bottomless, and I'm sure you understand now why we want to study acoustics and sound. So let's have a better look at the characteristics of sound. What we see here is a sine wave. This is the simplest sound we can encounter, and almost all sounds, no matter how complex they are, can be described by a sum of these simple wave functions. A is the amplitude of the sine wave. Well, the amplitude describes the range of the values the oscillated quantity can acquire. The unit depends on the quantity, and in sound we are quite often interested in pressure, so the unit is the Pascal. The dynamic range for humans, which is the range from the minimum to the maximum amplitude we can hear, spans an enormous range of about 10 million to 1. For this and more reasons, we use a logarithmic scale to describe it, and the unit of that scale is the decibel. On the right, we see a diagram with indicative sound pressure levels, measured in decibel, of various real-life sources. However, keep in mind that the actual levels depend on various factors, such as the distance from the source. We will not go into details, but it is interesting to note that the subjective perception of loudness is related to the sound pressure level, and thus the amplitude of a sound. Next is the frequency. The frequency of a sound defines the number of complete cycles, or repetitions if you like, the waveform performs in the unit of time. The completion of a full cycle is signified when the starting point is reached again along the periodic structure of the function. The unit is the hertz, which in the SI system of units is equal to 1/second. Now, frequency is inversely related to the period, which is measured in seconds. The period denotes the duration required for the sound wave to complete one full cycle. We have already mentioned that a sound can have many sine wave constituents. When this is the case, the period of the sound is the duration the aggregate wave function needs to complete one full cycle. Frequency is related to the subjective sensation of the pitch. Although not all sounds possess a clear pitch, at least for musical sounds, it is well correlated to the lower frequency present in that sound. Noise-like sounds, such as machinery noise, do not have a clear pitch. Noise can have a long-term negative effect on medical conditions, and this is one of the many reasons that people are interested in noise reduction. Human hearing is sensitive to a wide range of frequencies, with a nominal range for a healthy person ranging from about 20 Hz to 20,000 Hz, and this is about 10 times the frequency range of our vision. Next is the wavelength. The wavelength is the quantity that defines the length a wave disturbance travel in the time of one period. Well, of course, this depends on the speed of propagation. For airborne sound, This is considered to be constant for all frequencies, which is not necessarily the case for solids, where different frequencies may travel at different speeds. In air, the speed of sound depends on environmental parameters, such as the temperature, relative humidity, and atmospheric pressure. These relations are complex and stem from internal processing in the gas, so we will not go through them. So far, we have seen the most important characteristics of sound. So let's have a look at the behavior of sound when it travels from one point to another. So sound is linear, but what does that mean? One very important implication of linearity is that sound waves are superimposed in such a way that the amplitude at each point in space and time is the sum of all sound waves passing through that point at that instant. Quite simple, yet very powerful and important. In the animation, we see two sources emitting sound. Evidently, for some angles, the color of the pattern is white, denoting zero pressure, for all time instances. These are positions where the sound of the two sources interfere destructively. At these points, the sound generated by the sources will always meet with opposite amplitudes and, as we say, will cancel out. On the contrary, there are other points, such as midway and perpendicular to the axis connecting the sources. The disturbances will always meet with the same amplitude and will interfere constructively. The result is a constant increase of the combined amplitude. Another important and prominent phenomenon we have all experienced is the reflection of sound. Sound waves reflect when they meet a boundary or an abrupt change in the medium they propagate in. Most of us have heard an echo. This is the result of sound being reflected on some object at some considerable distance. In enclosed spaces, sound hits all boundaries, resulting in a large number of reflections reaching your ears with varied delays. This gives rise to the sensation of reverberation, which is the continuation of sound after the source has ceased. It is quite prominent in large spaces, such as cathedrals. So next, I'm going to talk to you about a phenomenon which is very important on the design of sound barriers, and this is diffraction. Diffraction is the bending of waves around the corner. The animation here will help us visualize it. The diffracting object, or let's say the edge of it, acts as a secondary source, which in a sense re-emits the impinging sound. In the animation, one would expect to have a quiet zone or shadow zone behind the perfectly absorbing barrier, but this is not the case. The edge of the barrier acts as a diffracting body and re-emits the traveling sound wave in such a way that it reaches the area of the expected shadow zone, albeit with decreased amplitude. Diffraction is a major factor in passive barrier designs and significantly affects their performance. Finally, I will talk to you about refraction. Refraction is the redirection of sound when the medium of propagation changes. The phenomenon depends highly on the properties of the medium, which in turn affect the speed of sound. Now, this means that refraction can happen even in the same medium if its properties are spatially varied. This is the case in the animation shown here, where outdoor propagation is simulated. Higher elevations exhibit higher sound speeds. The sound at the higher layers moves faster, and the bending of the wavefront is evident. In general, sound bends towards the areas of lower propagation speed. Now, before concluding this presentation, it is extremely important to state that the phenomena described here are frequency dependent. This is to say that the exact behavior will very much depend on the frequency of the sound. And as we already described, the frequency range of interest is quite large, and this really complicates things. Well, this is from me. Now Said will talk you through the different paths noise can follow until it can reach you.